So now that we've solved for our reactionary forces on our truss, what I'd like to do next is draw sort of a rough draft of our free body diagram. And what this allows us to do is kind of get an idea of the directions of all of our forces and help us decide whether the members would be under compression or tension. And we might get a couple of things wrong, but if we do, we'll get negative numbers later when we expect regular positive numbers. And then we can just update the free body diagram at that point. Let's go ahead and just draw out this rough draft. Let's draw what we know. Well, first off, we obviously know that we got 540 pounds going down at joint B. And we've got 60 pounds going to the right at joint D. That's what we were given. But then we solved for Ricky. Well, RCY, reaction force at joint C in the Y direction, we got 240 pounds going upward at joint C. And then we found out reaction force at joint A in the Y direction, or ray, we got 300 pounds going upward. And of course we got leftward force of 60 pounds at joint A to cancel out this rightward force here at joint D. And so all we have left is to draw the reactionary, not the reactionary forces, but the forces within the members acting on the joints themselves. So we've got member DC, for example, acting on joint C. The question is, will it be going down or up? Well, since 240 pounds is going up, that means this vector CD, has to be going down. And since it has to be going across this axis, sort of down and to the right or up and to the left, we can assume it's going down and to the right. So we'd say vector CD is going down and to the right at joint C. Well, it needs to cancel itself out, so it needs to go up and to the left at D, and we'd say vector CD, or member CD, I should say, is under compression. And you can see, well, the Y component of CD will be canceled out by this 240 pounds. But what about the X component of CD? Well, that'll be canceled out by BC, because we have another member here coming out of joint C, just member BC. And if it's being pulled to the left to cancel out this rightward force at joint C, the member itself has to cancel itself out. If it's being pulled to the left here, it has to be pulled to the right at joint B. And if it's being pulled inward, we can assume that joint BC is under tension. And if joint B is being pulled to the right at BC, it has to be pulled to the left somewhere else. And the only other place it can be pulled to the left is at member AB. And so we can say AB is under tension as well, because it has to be pulled inward in both directions to cancel itself out within the member itself. And it doesn't really matter which way you go next. I'm going to go ahead and go to A. But if you look at joint A, we got a rightward force and a leftward force, and those might cancel themselves out. They might not, because we don't know the amount that AB is. We don't know its magnitude yet. But I do know there is an upward force here at A. So we need a downward force canceling it out. And since the only other thing that is going down would be vector AD, it has to be going down and to the left. If it's going down and to the left here, it has to be going up and to the right at D. So that means that this is pushed outward. That means member AD has to be under compression. And of course, lastly, we got member B here, or I'm sorry, joint B. It's being pulled downward 540 pounds. That means it has to be pulled upward with the same force. We need a force pulling upward, I should say, but you might recognize what the force is already, because it's kind of obvious. But vector BD is being pulled up at B. That means member BD is being pulled down by D. And of course that makes sense, because we need a downward force canceled out by these two upward forces at AD and CD. That way it's not moving. That way we know, the bridge isn't flying away or falling apart. And that's how you draw a rough draft free body diagram of this truss.